Good day everyone. Welcome to Learn with MN. In this video, we're diving into one of the most exciting feature in Inkscape, tiled clones. This is a very comprehensive topic, so the tutorial will be way longer than the previous ones, but we have explained each tab and their option with examples in detail for the tiled clones dialog box. So, before getting started, if you're not familiar with clones and how they work, we recommend checking out our earlier tutorial on clones that breaks it all down for you. Its link is in the description. Let's start with what exactly is tiling. Well, tiling is simply covering a surface by repeating the same shape over and over, kind of like the tiles you see in a bathroom. The same idea applies in Inkscape, except here, those tiles are just clones of a single object. Now, this is where the magic happens. Inkscape gives you a ton of control over how you create those tiled clones through a feature called the Create Tiled Clones dialog. This tool lets you not only replicate your object, but also customize how those clones behave. You can adjust their size, position, rotation, and so much more. It's like having unlimited creative options at your fingertips to make patterns and designs. To access this tool, go to the Edit menu, then Clones, and then select Create Tiled Clones. Once you open the dialog, you'll see several tabs, each packed with different options to fine-tune your clones in different ways. Let's discuss each one by one in detail. Before we move forward, let's discuss these fixed options that are available across all the tabs in the Create Tiled Clones dialog. These options at the bottom are the same for each tab, and help you decide the size of the tiling, either by specifying the number of rows and columns, or by setting the width and height of the area you want to fill. For example, without changing any other settings, if I enter 2 rows and 3 columns and click Create, it will generate a tiling of the selected object with 2 rows and 3 columns, like this. There are 7 tiles in total, 6 of them are clones, and the one that remains selected and is behind the first tile is the base object, or as we sometimes call it, the parent object. You can move the parent object aside to make changes to the clone tiles, like resizing or adjusting the fill and stroke. Any changes you make to the parent will be reflected in all of its clones, like this. Alternatively, by selecting width and height, you can specify the exact area you want to fill with the clones of the selected object. For example, if I set the width to 250 mm, and the height to 130 mm, and then click Create, it will generate a tiled clone pattern that covers the specified area. The Remove button allows you to undo or remove the tiling, but this only works if the base object used for the tiling is selected, like this. This option called Use Saved Size and Position of the Tile forces the tiling to use the size and position of the base tile from which you created a tiling last time, instead of using the current size. For example, let's duplicate this object and change its height, like this. I'll duplicate it again and set it aside here. Now, if I create tiles for this one, the result will look like this, as expected. Let's create tiles for this too. Now, if I check the Use Saved Size and Position box, and create tiles for this object, the one where we changed the height, you'll notice a different result. That's because we saved the size and position of the previous base object. This is useful if you want to maintain consistent spacing between tiles, even if the bounding box of the base tile changes due to editing, as we did earlier by adjusting the height. Next is the Unclump button, which spreads out the clones randomly to reduce the spacing between them, like this. You can use it repeatedly by clicking again and again to see different results. Lastly, the Reset button restores most of the settings in these tabs to their default values. Now, let's move on and explore each tab to see how they work. The first tab we'll look at is the Symmetry tab. This is the core of the tiling process, and probably the most essential part of creating tiled clones. The Symmetry tab lets you define the basic arrangement and symmetry of your tiled clones. Essentially, it helps create patterns that repeat regularly to cover a surface without gaps or overlaps. These symmetries are found in tiling with shapes like triangles, rectangles, parallelograms, and hexagons. To create these patterns, there are 4 key symmetries you need to understand: translation, rotation, reflection, and glide reflection. Each of these symmetries determines how an object or motif is repeated to form a pattern. Using these 4 symmetries, there are a total of 17 possible ways to create tiled patterns. These 17 tiling symmetries are known as wallpaper groups, and all of them are available in the Symmetry tab's drop-down menu. But before we dive into each wallpaper group, let's first break down the 4 main symmetries that make these patterns possible. First, we have the translation. In translation, the pattern repeats in a straight line without any rotation or flipping. For example, take a look at these identical squares, arranged side by side. This is an example of translation, where the squares form a seamless pattern. Next is rotation. Here, the pattern rotates around a fixed point at specific angles like 90 degrees, 120 degrees, or 180 degrees. This allows the pattern to repeat smoothly around that point. For example, if we take this object and rotate it 180 degrees around a central point, it will form a pattern like this, with 180 degrees rotation. Third, we have reflection. In reflection, the pattern is flipped across a line, creating a mirror image. For instance, if we reflect this object across a line, we'll get an identical but mirrored version of it, and the pattern created through reflection will look like this. Finally, there's a glide reflection. This is similar to mirror reflection but with a twist: the mirrored object also slides, or glides, along the line. So, it's a combination of reflection and translation. A perfect example of glide reflection is footprints. The left and right footprints are mirror reflections of each other, but they're also glided forward to form a continuous path. For example, if we take this object, then it will form a pattern like this, with glide reflection. The 17 wallpaper groups represent all the ways you can tile a flat surface with repeating patterns using translations, rotations, reflections, and glide reflections. Let's discuss each, and break them down into categories based on the symmetries they use. The first symmetry is P1. The P1 symmetry is a simple translation symmetry where the base tile is duplicated without any rotation or reflection. It's a basic repeating grid pattern. Whether the tiles are spaced out, close together, or shifted horizontally or vertically, the pattern remains P1 because there's only translation symmetry with no rotation or reflection. For example, if we use this as a base tile, the 4x4 result with P1 will look like this. P2 symmetry involves both translation and 180 degrees rotation, but no reflection. Each time the base tile repeats, it is rotated by 180 degrees. For example, starting with this base tile, the second tile is rotated 180 degrees, and the third tile is also rotated 180 degrees from the second. The pattern continues in this way. If we use this base tile with P2, the 4x4 result will be like this. The PM symmetry includes translation and reflection across a line, but no rotation. The base tile is mirrored across a line as it repeats. Starting with this base tile, the first tile is reflected to form the second, and the second tile is mirrored again to form the third, continuing the pattern. If we start with this base tile and select PM, the 4x4 result will be like this. PG symmetry combines translation and glide reflection, with no rotation. Glide reflection means the base tile is reflected horizontally, and also shifted along the line as it repeats. Starting with this base tile, it is reflected, and glided to form the second tile. Similarly, the second tile is mirrored and glided to form the third tile, thus the pattern continues. If we start with this base tile and select PG, the 4x4 result will be like this. CM symmetry is combination of 3 symmetries: translation, reflection, and glide reflection, but no rotation. The base tile is not only mirrored along the line, but its reflection is also shifted along the same axis. If this is the base tile, it is reflected to form the next column tile, and reflection is glided along the line to form the next row. Similarly, the second tile is mirrored to form the third column, and reflection is also glided to form the next row tile. The pattern continues in this way. If we start with this base tile and select CM from drop menu, the 4x4 grid result will be like this. PMM symmetry includes translation and two perpendicular reflections. The base tile is mirrored both horizontally and vertically. Starting with this base tile, it is mirrored horizontally and then vertically to create the next tiles. The pattern continues in this way. If we start with this base tile and select PMM from the drop-down, the 4x4 result will be like this. PMG symmetry includes translation, 180 degrees rotation, and reflection. The base tile is rotated 180 degrees along one axis, and reflected along another. If this is the base tile, it is rotated 180 degrees along the horizontal axis, and reflected along the vertical axis. The pattern repeats in this way. So, if we use this base tile and choose PMG from the drop-down, the 4x4 result will look like this. PGG symmetry involves translation, glide reflection, and 180 degrees rotation. The base tile is mirrored, then glided along one axis, and rotated 180 degrees along the other axis. There is no pure reflection in this symmetry. For example, starting with this base tile, it is reflected vertically, then glided along the horizontal axis, and rotated 180 degrees along the vertical axis. The pattern continues in the same way. If we use this base tile and choose PGG from the drop-down, the 4x4 result will look like this. CMM symmetry combines translation, two reflections, and a 180 degrees rotation along a diagonal axis. The base tile is first mirrored horizontally, then vertically, and finally rotated 180 degrees along the diagonal. All groups we discussed till now were giving one or two variations of base tile. But in this symmetry, the base tile gave us three variations making a 4-tile block. If we start with this base tile, it is reflected horizontally, then vertically, and rotated diagonally. The process repeats. If we use this base tile and choose CMM, the 4x4 grid result will be like this. P4 symmetry includes translation and 90 degrees rotation without any reflection. The base tile is rotated by 90 degrees horizontally, then this is rotated by 90 degrees, and then this is rotated by 90 degrees. This creates a 1x4 tile block that is repeated to form a pattern. To complete the cycle, 4 rotations are needed, which results in 4 variations of the base tile. If this is the base tile, the 4-tile block is repeated to form the pattern. This symmetry works best with the square tile designs. So, if we have this as a base tile and select P4 from the drop-down, the 4x6 grid will be like this. P4M symmetry includes translation, 90 degrees rotation, and reflection. In other words, it is a combination of P4 and its reflection. The base tile first is rotated by 90 degrees 4 times to complete the cycle. Then it is mirrored to create the P4M pattern. For rows and columns, you may find it confusing at the start, but on the whole, it is a combination of P4 and its reflection. Starting with this tile, it is row 1 in column 1, then row 1 in column 2 will be its reflection along its diagonal axis, like this. Similarly, row 1 in column 3 will be a 90 degrees rotation of the base tile, then row 1 in column 4 will be its reflection along the diagonal axis, like this. The pattern continues in this way. If you observe the pattern, this is the P4 symmetry of the base tile and this is its reflection. This symmetry works best with right-angle triangle tile designs. So, if we have this as a base tile and select P4M from the drop-down, the 4x8 grid will be like this. P4G symmetry includes translation, 90 degrees rotation, and 2 reflections. If this is the base tile, then, this is the pattern we get after 90 degrees rotation. If we mirror this block horizontally and vertically, we get the P4G symmetry. In this pattern, rows and columns work differently. For example, this is row 1, and this is row 2. But in columns, this is column 1, column 2, column 3, and column 4. Similarly, this is column 5, column 6, column 7, column 8, and so on. In this 2x12 setup, after every 4 columns, the tiles are reflected both horizontally and vertically. If we have this as a base tile and select P4G from the dropdown, the 2x12 grid will be like this. P3 symmetry includes translation and 120 degrees rotation, but no reflection. The base tile is rotated by 120 degrees at a fixed point, then this is rotated by 120 degrees. This creates a 1x3 tile block that is repeated to form a pattern. This type of symmetry works best with parallelogram shapes like rhombus. To complete the cycle, 3 rotations are needed, resulting in 3 variations of the base tile that repeat to form the pattern. The rows and columns work the same as in P4G symmetry. If we have this as a base tile and select P3 from the dropdown, the 3x12 grid will be like this. P3M1 and P31M symmetry both include translation, 120 degrees rotation, and reflection. In other words, it is a combination of P3 and its reflection. The base tile first is rotated by 120 degrees 3 times to complete the cycle. Then each variation is mirrored to create the P3M pattern. Both P3M1 and P31M have the same symmetry but give slightly different results. With this base tile, P3M1 creates a scattered pattern like this. And for P31M, the pattern is dense, like this. Both are 2x12 patterns for the given base tile. P6 symmetry includes translation and 60 degrees rotation, but no reflection. The base tile is rotated by 60 degrees at a fixed point, then this is rotated by 60 degrees and it repeats until the full cycle is complete. This creates a 1x6 hexagon tile block that is repeated to form a pattern. This type of symmetry works best with an equilateral triangle tile design. To complete the cycle, 6 rotations are needed, resulting in 6 variations of the base tile that repeat to form the pattern. If we have this as a base tile and select P6 from the dropdown, the 2x18 grid will be like this. Finally, the last symmetry is P6M. It includes translation, 60 degrees rotation, and its reflection. In other words, it is a combination of P6 and its reflection. The base tile first is rotated by 60 degrees 6 times to complete the cycle. Then each variation is mirrored to create the P6M pattern. So total of 12 tiles together form the hexagonal tile pattern, which is repeated to form a pattern. If we have this as a base tile and select P6M from the dropdown, the 2x24 grid will be like this. The second tab we'll look at is the Shift tab. The Shift tab allows you to adjust the spacing between tiles, letting you control how each tile in your pattern shifts horizontally or vertically, relative to the previous tile. By default, there's no spacing between tiles. It provides options to shift tiles per row or column, with some additional settings. Let's discuss each one by one. Shift X controls the horizontal shift of tiles along rows and columns, with values entered as percentages. Shift X per row shifts each tile in a row horizontally based on the percentage value. For example, if Shift X per row is set to 50% and we create a 5x5 grid of squares, each row shifts 50% of the tile's width to the right, compared to the previous row, creating a staggered horizontal effect. Positive values shift right, while negative values shift left, like this. Shift X per column shifts each tile in a column horizontally based on the percentage value. For example, if Shift X per column is set to 50%, each tile in the column shifts right by 50% of its width, compared to previous column, like this. Randomize option randomly shifts each tile horizontally within a specified range. If Shift X randomize is set to 20%, each tile will move left or right by a random value between -20% and +20% of its width. Shift Y controls the vertical shift of tiles along rows and columns, based on the percentage values. Shift Y per row shifts each tile in a row vertically based on the percentage value. For example, if Shift Y per row is set to 50% and we create a 5x5 grid, each row shifts down by 50% of the tile's height, compared to the previous column. Shift Y per column shifts each tile in a column vertically based on the percentage value. For example, if Shift Y per column is set to 50%, each tile in a column shifts down by 50% of its height, compared to the previous column. Similar to Shift X, the randomize setting for Shift Y shifts each tile vertically within a given range. For example, if Shift Y randomize is set to 20%, each tile will move up or down by a random value between -20% and +20% of its height. The exponent setting defines whether rows or columns are evenly spaced or not. By default, its value is 1 for both rows and columns, meaning each row and column has even spacing. Values greater than 1 create divergence, where the spacing between rows or columns gradually increases. For example, if you set the row exponent to 1.2, each row will be spaced farther apart as you move down. Values less than 1 create convergence, where the spacing between rows or columns gradually decreases. For example, setting the row exponent to 0.8 reduces the spacing, bringing each row closer as you move down. The same applies to columns. Values greater than 1 will diverge the columns, while values less than 1 will converge them. The alternate option works in combination with Shift X, or Shift Y, or both. If the shift values are set to 0, this option will have no effect. When enabled, the shift alternates between being added and subtracted for each row or column, creating a back-and-forth pattern. For example, if Shift X per row is set to 50%, an alternate is enabled for rows, the first row will shift 50% to the right, the second row will shift -50% to the left, and so on. This results in a zigzag pattern along the horizontal axis. Similarly, if Shift Y per column is set to 50% with alternate enabled for columns, the first column will shift 50% down, and the second column will shift -50% up, creating a zigzag pattern along the vertical axis. The cumulate option adds each previous shift to the next shift, creating a cumulative effect along rows or columns. If you apply Shift X per row by 10% without cumulate, the first row stays in its starting position, and each subsequent row shifts by an additional 10% to the right. With cumulate enabled on rows, each shift also includes the previous row's shift. For example, the first row has no shift. The second row shifts by 10%, the third row shifts 20% plus previous row shift that is 10%, so it will shift by 30%. Similarly, the fourth row shifts 30% plus previous row shift that is 20%, so it will shift by 50%, and so on. Keep in mind that the cumulated shift is based on adding the individual shift values for each row, not the cumulative shift value of the previous row. Similarly, you can apply cumulate shift on columns also by enabling this option. Next is exclude. This setting lets you exclude the width or height of tile spacing. For example, if I check exclude height and create a 5x5 grid with no shift values, you'll see the result looks like a 1x5 grid. The tiles are still total 25, but each row is stacked on top of the first row, aligning with their respective columns. Similarly, if I check exclude width instead, it'll display as a 5x1 grid, with each column stacked over the first column, aligned with their respective rows. You can adjust shift values to explore different effects when using this setting. Moving to the Scale tab. If you've got the Shift tab, then understanding the Scale tab will be very easy. The Scale tab adjusts the size of tiles horizontally, vertically, or both. To show the impact of each setting here, I've set Shift X per column and Shift Y per row to 80% so we can see clear differences. Scale X adjusts horizontal scaling along rows and columns. For example, if I set scale X per row to 10%, each tile in a row increases in width by 10% compared to the row above it, giving a tower-like effect. Positive values increase the size, while negative values shrink it. Scale X per column scales each tile horizontally along the column. If I set scale X per column to 10%, each tile increases by 10% in width compared to the first column, creating a growing width effect down each column. Randomize randomly increases and decreases the size of each tile. For example, if we set scale X randomized to 20%, then each tile will be resized by a random value between -20% and +20% of its width, like this. Similarly, there is scale Y, with the only difference that scale X causes change in width, and scale Y causes change in height. Next is the exponent. The exponent controls how quickly or slowly the scaling changes across rows or columns. By default, its value is 1. With an exponent of 1, the scaling increases uniformly. For example, if you set scale Y per row by 5%, each clone will increase by the same percentage compared to the previous clone. This is linear scaling, where each step adds the same percentage increase. When the exponent is greater than 1, the scaling grows faster as you move down the rows or columns. This creates a diverging or accelerating scaling effect. As the exponent increases, the rate of growth becomes more rapid with each row. The scaling starts more gradually but grows more aggressively. When the exponent is less than 1, the scaling increases more slowly with each row or column. This is called converging scaling because the rate of growth decreases progressively. The growth starts more rapidly but slows down over time, causing the size differences between rows to become smaller. The base value alters the scaling pattern based on a logarithmic spiral concept. When you scale with a base value, the rate at which each next row's or column's size increases or decreases is affected logarithmically. This means the growth rate changes in a slower or faster manner depending on its value. By default, it is 0, which means the base is not used, and the growth rate follows a simple linear pattern. Each row or column is scaled by the same percentage consistently. When the base is greater than 1, the scaling grows at a critical rate. Initially, the increase in size is very slow, but it gradually picks up speed. When the base is less than 1, the scaling shrinks at a critical rate. The size decreases sharply at first, and then the reduction slows down progressively. Now, you may be wondering what the difference is between the exponent and the base. Exponent scaling increases or decreases the size exponentially, which means it gives a uniform or predictable curve in scaling changes. Base scaling works logarithmically, so the growth rate is more gradual, and changes take longer to have an impact. It gives a gradual or smooth transition, making the scaling less abrupt at the start but accelerating or decelerating based on the base value. You can directly control how fast the scaling grows or shrinks with the base value. To learn more about exponent and base and how their values are calculated, keep visiting our website. A comprehensive guide with a complete explanation will be uploaded soon. Next is alternate. It is the same as what we discussed in the Shift tab. With this option, the scaling of clones is applied on alternate rows or columns. If we set scale X per row to 50% and check this option, scaling will be applied on alternate rows, like this. Similarly, if you set Shift Y per column to 50% and check this option, then scaling will be applied to alternate columns, like this. Next is cumulate. It is the same as what we discussed in the Shift tab. With this option, the scale percentage of the previous row is also added to the scale percentage for each row. For example, if we set scale X for rows to 10% and enable this for rows, you will see the first row is of original size, meaning no scale, and the second row is scaled by 10%. But for the third row, it will scale by 10% plus the scale percentage of the previous row, which is 10%. So, it will scale by 20%. Similarly, the next row will scale by 30% plus 20% of the previous row, so it will be by 50% and so on. The next tab is the Rotation tab. The Rotate tab is used to rotate tiles clockwise or counterclockwise based on their position in rows or columns. The rotation center is used as the center of rotation. The angle is used to define the degree to which you want to rotate. If I set the angle to 30 degrees per row, then the result will be like this. Each successive row is rotated by 30 degrees. Similarly, if I set 30 degrees per column, then each next column will be rotated by 30 degrees, like this. Like scale and shift, you can also randomize the rotation by giving a value in percentage, and it will assign random rotation values to each row or column. The next two options work the same as discussed earlier. Alternate will apply rotation on alternate rows or columns, and cumulate will rotate cumulatively. The Blur and Opacity tab is used to increase the blur and decrease the opacity of clones for each row or column. If we set blur to 5% per row, then the square in each row is blurred by 5% more than the first row, like this. Similarly, this applies to columns. Randomize will blur each tile by a random value based on the percentage value we enter. For instance, if we set randomize to 10%, then each tile will be blurred by a random value between 0% and 10%, like this. The same concept is for opacity, with the only difference being that blur increases, and opacity will decrease by the given percentage. If we set the opacity to 10% per row, then the opacity of the square in each row is lowered by 10% more than the first row, like this. The circle is created behind the tiles to show the clear difference in each opacity level. Similarly, this applies to columns. Randomize will lower the opacity for each tile by a random value based on the percentage value we enter. Alternate will apply blur and opacity on alternate rows or columns based on which option you select. The Color tab is used to change the color of each tile depending on its position in rows or columns. The color change is specified by altering three components of color with HSL standards. H is for hue, S is for saturation, and L is for lightness. Before moving forward to see its effect, there are two important factors. First, the fill and stroke should be set to unset. If not, this whole tab will not work. Secondly, initial color must be specified by clicking this color button. This color will specify the starting color. Let's say I select red as the initial color. If I set hue per row to 10%, then the result for 5x5 will be like this. Hue changes the color of each row by 10%. Here, there is no change in saturation or lightness. Saturation specifies how vibrant the color will be. A greater value makes colors vibrant, and a lower value makes them dull and closer to gray shades. Red is already a vibrant color, so if I revert hue back to 0, and set saturation per row to -10%, the result will be like this. Lightness specifies the brightness of the color. A greater value makes it lighter and closer to white, and a lower value makes it darker and closer to black. If I set lightness to 10% per row, the result will be like this. You can play with these values to get amazing results. The same applies to columns. For instance, if I set lightness per row to 10% and lightness per column to -10%, the result will be like this. This will create different shades of red, which can help you create color palettes. Randomize and alternate work the same as discussed for previous tabs. Randomize will assign random values, and alternate will apply changes to alternate rows or columns. One thing to note is to avoid setting the starting color to black or white if you're only changing the hue, as it will not affect any tile. This is similar to trying to walk east from the North Pole. Finally, last but not least is the Trace tab. The Trace tab is used to set the color, size, and transparency of the clone tiles, based on the color and transparency of the objects, or even images placed behind these tiles. That's why it is called tracing, as it shows the result based on the reference behind each tile's position. To make this tab work, make sure this checkbox is checked. The Trace tab has 3 sections. Pick from the drawing specifies which property of the underlying object will be used for input. Options include color, opacity, and each component of RGB and HSL. Color picks the visible color and its opacity from the source drawing. Opacity picks only the opacity value from the source, ignoring color information. R, G, and B options pick the red, green, or blue channels from the RGB color model of the source, respectively. Each picks the color intensity of their respective channels. H picks the hue from the HSL color model, while ignoring saturation and lightness. S picks the saturation value from the source by determining how vibrant or muted the color is. L picks the lightness value from the source by determining how light or dark the color is. The second section is Tweak the picked value. These options allow you to modify the values you've picked from the drawing before applying them to the clones. It includes Gamma Correct, Randomize, and Invert. Gamma Correct changes how colors or values spread across the clones. When gamma is above 0, it makes mid-range values brighter or more intense. When gamma is below 0, it makes those mid-values darker or less intense. Randomize adds randomness to the values you pick, so the clones don't follow an exact pattern. Instead, they vary in unpredictable ways, depending on the value you choose to randomize. Invert inverts the picked value before applying it to the clones. For example, if you're picking opacity, an area that's fully opaque in the source will turn fully transparent in the clone, and a fully transparent area will become fully opaque. The third section is Apply the value to clones. These checkboxes determine how the picked and possibly tweaked values affect the clones. Picked values can affect the presence, size, color, and opacity of the clones. Presence controls whether a clone will be created or not, based on the picked value. The probability of creating a clone depends on the picked value from the source object. Brighter or more intense colors lead to more clones, while lighter or less intense colors lead to fewer or no clones. Size adjusts the size of each clone based on the picked value. Color applies the picked color to the clones. Each clone will inherit the corresponding color from the source object based on its position. But this option will only work when the base tile's fill is set to unset. Opacity applies the opacity value to each clone based on the picked color. Each clone's transparency will be adjusted based on the input value from the source underneath each clone. Let's discuss each with different scenarios. Starting with color. Let's say we have a red to white gradient rectangle as background, and this green circle as a base tile. If we don't change anything in the Tweak the Picked Value section, and select the presence, the result will be like this. Clones will appear based on the intensity of the color. As red is more intense, so more clones will appear in red areas, and fewer or no clones will appear in light areas. If we select the size and create clones, the result will be like this. As input is color and red is more sharp and intense, so the clones in red area will be larger and become smaller as move towards the white. For color output, first set the fill of the base tile to unset. Now, if we check the color option, each clone will adapt the corresponding color from the source, like this. If we select the opacity, it will change the opacity of each clone based on the colors, like this. If we select size, and change the gamma correct value from 0 to 1, the result will be like this. As you can see, the size of clones is increased as compared with a value equal to 0. Similarly, if we set a value less than 0, then the clone size will become more small, like this. If we set randomize to 10%, it will randomize the picked color, which will change the size of clones randomly, like this. If we check the invert option and create tiles, you will see that now the clone size is larger where it was smaller, and becomes smaller where it was larger earlier. Let's see how opacity works. Let's say we have this gradient rectangle as a background, where this end has less opacity, and this end is fully opaque. This green circle is a base tile. If we don't change anything in the Tweak the Picked Value section, and select the presence, the result will be like this. Clones will appear based on the opacity of the picked color. More clones will appear in fully opaque areas and fewer to no clones will appear in transparent areas. If we select the size and create clones, the result will be like this. The clones in fully opaque areas will be larger and become smaller as moved towards the transparent areas. If we check the color option, each clone will adapt the corresponding original color from the source, not its opacity, like this. If we select the opacity, it will change the opacity of each clone based on the opacity, like this. Let's say we have this red-green-blue gradient rectangle as a background. If we select R as input, and select the presence, the result will be like this. As red is selected as input, so more clones will appear in red areas, and fewer to no clones will appear in other color areas. If we select the size, the result will be like this. The clones in red areas will be larger and become smaller as moved towards the other color areas. For the color option, each clone will adapt the corresponding color from the source, like this. If we select the opacity, clones will be more opaque in red areas and become transparent in other color areas. The same results will be received for G and B in the green and blue areas respectively of the gradient. Let's say we have this gradient rectangle as a background. If you look at the hue value for each color in the Fill and Stroke tab, you will notice that this color has the smallest hue value. Then this color has greater than this, and the third color has the highest hue value. So, if we select the H as input, then the color with the highest hue value will have the most clones, larger clones, and most opaque clones based on the options we select, like in this example. The same theory applies to saturation and lightness. You can play with these options with different backgrounds to see different and interesting results. You can also select multiple options to see their effect together. That's why this dialog box is so important, as it gives you a variety of options to get amazing results. That was all for this video. If you have any queries, feel free to write in the comments section or contact us on our website. Its link is in the description. If you like this video, please like, subscribe, and hit the bell icon so you don't miss any updates. Thank you for watching.